Okay, so these are the static equilibrium examples, part A. And so this is one of the most common things we think of when we think of using 2D vectors in engineering. It says we've got a 1,000-kilogram object that's suspended from two equal length cables such that each cable makes a 45-degree angle with the ceiling. Determine the tension measured in newtons in each cable. So, quick sketch of what's going on. We've got a ceiling here. We've got some weight that's 1,000 kilograms. We've got these two cables that make 45-degree angles holding it up. And so what we want to do is determine what forces are going on here in the two tension cables. And so we've really got, we want to draw our free body diagram. So we'll make an axis. And remember, we always get to pick the origin, and so the best place to put the origin is where the stuff is happening. And so really what's going on is everything's kind of coming together right there. So that's going to be our origin. And so from the origin, we've got basically three forces acting on it here. We've got T1, which is the tension coming out of that cable. We've got T2 pulling up and back this way. And we know each of these is 45 degrees. And then we've got the weight of the object pulling down there. And we don't know these two, but we know the weight of the object is 100 kilograms. But if we're talking about 100 kilograms, we're going to talk about forces. And so how do we get force? We have to remember that force is equal to mass times acceleration. In this case, acceleration, what's pulling it down is gravity. So that's equal to 9.81 meters per second square. And so our force, our weight is actually 100, or I'm sorry, 1,000 kilogram mass times 9.81 meters per second squared, which would give us 9,810 kilograms meters per second squared. And of course, kilograms meters per second squared is a newton. So our weight is actually 9,810 newtons is what we're working with this. Alright, and so remember again, in order to, if we have static equilibrium, that the sum of the forces equals 0. So the sum of the forces in the x direction and the sum of the forces in the y direction all have to equal out to 0. So if we look at the forces in the x direction, well, in the x direction we have T1 times the cosine of 45 degrees. T2, a couple different ways to look at that. One is that we could look at it as this entire angle here, which would be 180 minus the 45 degrees. So that would be 135 degrees. And so that's the generally what we want to talk about. Like we always want to talk about points from this. What you may see some people another way to solve this would be, or we could say minus the cosine of 45 degrees. Because if we look at it just from being this triangle and use this angle, we talked about this back when we were breaking down, when we were creating our equations to talk about these, that if we use this angle, we just have x going in the wrong direction, so we'd have to subtract it instead of adding it. And we should see that those come out to be numerically the same. So we know that T1 times the cosine of 45 plus T2, I'm going to put times the cosine of 135, has to equal 0. If we get what those are, it will tell us that cosine of 45 is 0.707 times T1, and the cosine of 135 is negative 0.707 T2 equals 0. So we have one equation that tells us that those two things add up to be 0. If we look at the forces in the y direction, we have T1 times the sine of 45 plus T2 times the sine of 135 minus W, because all of W is going downward, acting against it. So we know that that has to equal 0. So then T1, so let's get some numerical values in for this. We know that sine of 45 is also going to be 0.707 times T1. Sine of 135 is going to also be positive 0.07 times T2 minus, our weight was 9, 8, 10, has to equal 0. So we could rewrite this equation as 0.707 times T1 plus 0.707 times T2. I'm going to move this to the right side of the equation, has to equal 98.10. The good news about this, so now if we remember back to things we did a few weeks ago, what we essentially have are two equations and two unknowns. So several different ways to solve that. One of the easiest ones, and I'm going to line it back up over here, solve for T1 and T2. And again, this isn't the best way to kind of keep up with these things. But I know that 0.707 T1 minus 0.707 T2 equals 0. And what I also know is that so this is from the sum of forces in the x direction. This is from sum of the forces in the y direction. That 0.07 plus T2 is equal to 9, 8, 10. That they have to be pulling up that entire weight between the two of them. So pick our method to solve it. The easiest one, since these have the same coefficients, is to just add the two equations together. We'll see T2 go away, and we can get T1 quickly. So 1.414 times T2 plus T1 plus 0 times T2 is 98.10. And so T1 is 98.10 divided by 1.414. So I get it 69.38. Units are newtons. I can plug that back into either equation and get what T2 is. I'm going to plug it into this one because it's a little less things. So 0.707 times 69.38 minus 0.707 times T2 equals 0. Actually, if we do the, instead of actually multiplying it out, I'm recognize that the coefficients are kind of the same. If I move that to that side, it's the same as 0.707 T2. If I divide everything by 0.707, I get that 6938 has to equal T2. Which it's not surprising that since we have cables of equal length at the same angles, that we get that the tension is the same in both of them. So our final answer is that T1 equals 6938 newtons and T2 equals 6938 newtons. And possibly because of the amount of rounding we had in there before, you might want to just round that to 3 sig figs, makes it 6940. Again, just make sure you're getting the right number for what you're being asked to put in.